Thank you for joining us for today's presentation entitled The Vast Possibilities of Agent-Based Modeling. And allow me to introduce today's presenter, Dr. Lars Mortensen. Lars has a research background in ecosystem ecology, including multiple ecosystem types ranging from high Arctic to subtropical zones. He also has extensive knowledge of statistical modeling. His current focus is on the application of agent-based models and species distribution models to the impact of anthropogenic noise on marine life. And with that, I now hand it over to you, Lars.
Thank you very much, Barbara. Yes, hello everybody, and welcome to the living room of me. Yeah, it's afternoon here in Denmark, where I'm situated, and so I'm having it from the home office, which is kind of nice. And Barbara did a very nice background on on me, so I'll just dive right into it. So the vast possibilities of agent-based modeling. I'm pretty sure most of you know what an agent-based model is, even though you say that maybe you don't know that it's an agent-based model, but all of you have encountered an agent-based model at some point in your life. And one of the best examples of an agent-based model is this, for instance. This is a cutscene from the movie Lord of the Rings. Very big movie that was made early on. And agent-based models come in here because they found it quite a hassle to make movies entailing where you had to animate this amount of people to make it credible. The problem is that if you have to animate a lot of people, you have to make them do individual things, because if you don't make them do individual things, it won't seem very realistic. So in this movie, they actually applied agent-based models. It has been done in other movies as well. So in here, the function behind these ones are actually a small model for that entails a stochastic behavior for each of the people you see here, or the animatrons, and then they run the agent-based model, and then they'll act the behavior that they were coded to do, and you actually get very nice scene from that. So that's actually a good example of an agent-based model used in real life. We're not going to talk about movies, of course. We're going to talk mainly about agent-based model in the Mike software that we use here in DHI to make our models. And so the purpose. What is the purpose of the presentation? Well, it's basically to demonstrate some of the possibilities that agent-based model can be used for. We're going to look a little bit into the functioning of an agent-based model, how it is constructed, and then we're going to look a little bit about how to view and interpret agent-based model output, but we're just going to touch shortly on that. And as Barbara said, my name is Lars Mortensen. I have a PhD in spatial ecology here in Denmark. I've been working with agent-based models for some time now in different environments and with different species. But to start at the start, what is a model? I think any modeling presentation should always start out with this. What is the model? Because I think when you mix people from different backgrounds, there's always a bit of confusion what people think a model is, because it differs between different backgrounds and different sciences what a model can be. But if you view a model, if you boil it down to the essence of a model is a representation of some element of the real world, usually a simplification. That means, as here, real world is a cat. Garfield is a simplification of that cat. He doesn't have all the nuances of the cat, and he doesn't have all the fine details of cat, but he is a model of a cat. In ecology, this means something else. For instance, here you see a natural system with the variation. This is the data on fur trade, I think from Canada, on the Canadian lynx and the snowshoe hare. You can see how it fluctuates together in a classic Predator Bay fluctuation model. So a model would be like this. So this is the simplified version of what we saw in the other one. So that is a model of something, an element of something in the real world. And it usually has the aim of solving some sort of a problem. But the thing is, with most of these models, population models, as you can call them, the instance of the predator-prey model is that they always assume all individuals within the populations are the same. It's what we call a top-down model, meaning that you view the population from the top, and then you assume all individuals have more or less the same properties, the same birth rate, the same death rate, fluctuation rates are the same, and from that you use you interpolate some sort of a population development or change or consequence, depending on what you want to calculate. However, it is certain that most population will have some sort of a variation within the populations. For instance, like this. But if you extend that, the likelihood that most populations are more like this, with a large variation between individuals, individual behaviors, sizes, life rate, birth rates, everything is just different within the population. So this is where the agent-based model come in. The agent-based model is a bottom-up model that essentially is defined by this. It's a model describing the autonomic behavior and states of agents, objects, or individuals. This means that instead of viewing a population from top up and viewing on all parts of the population at once, you view it from the bottom up, and then you simply look at the individual behavior, and then you kind of combine that and have some emerging probabilities from that kind of modeling. We'll go a little bit deeper into that in a bit. But what can be modeled by using ABM Lab in Mike or an agent-based model? Well, given the definition before, then anything that you can treat as an individual or an object, you can model as an agent as well. That means that this goes from anything from blue whale, ocean-going tanker, to life rafts, to individual fish, to individual flowers. And even down to one of the things that we do in DSI is also model oil spills in an agent-based model, because you can treat the oil globules, I think I mispronounced that probably, you can view them as being individuals because they have a limited amount of space they occupy. Things dissolved in other things, like chemicals dissolved in water, it's really hard to treat that as individuals. This means that things like pollutants being dissolved in water spills is not very good at being modeled in a agent-based modeling, because it's hard to actually define what is an individual in this population. So that's kind of the differences between the two. Here in DHI, we use a little bit of a special framework for using agent-based model. And we set up our Mike software to combine this very seamlessly together, which is very nice. The thing is, here in DHI, we couple output from our Mike 3FM, our hydrodynamic model, and we couple that to statistical and dynamic habitat mapping. And then we couple both the hydrodynamics and the dynamic habitat mapping to our agent-based models, meaning that we can supply our agents with information both from standard top-down population modeling, dynamic habitat modeling, and also from dynamic hydrodynamics, which changes in space and time. This gives this platform a very, very good, a solid basis to do agent-based model, because you can actually inform your agents a lot through this combination. So an agent-based model in its core, what does it look like? Well, it's this is a Lagrangian representation in Mike, and essentially It means that each agent you put into into an agent-based model will typically have an XYZ component. Uh, it will occupy space. It doesn't need to occupy space. You could do agent-based model without having a spatial component in it. But usually in the work that we do at DHI anyway, we have a spatial component in our models. Then each agent will also have elements of movement. It will somehow through some algorithm obtain a direction and a speed where it will change its change space it's occupying. Then it can also have a range of states. States, that's internal compositions that can change in time. That can be volume, that can be mass, that can be volume, mass, etc. Other things that apply to the state of the body or the state of whatever component it is you're modeling. Then in this we also have feedback between the Eulerian and the Lagrangian framework. That means that the agent-based model, which is typically Lagrangian, will be able to absorb information from the Eulerian framework that is occupying. That means that the space that it surrounds. It's also possible to do that the other way, to make the Eulerian framework absorb information from the Lagrangian, for instance, simulate food depletions or similar things. And then it also contains some rules on death, birth, etc., etc. So in relating to the survivability of the agents. And lastly but not least, it's in the modeling that we do in DHI, it's independent of the model grid. That means it doesn't matter what the resolution of the space that the agent is occupying. It's only actually just something about how it moves itself. So all of these components you model for one individual, one agent. And then when you press play for an agent-based model, you take a lot of these and put them together. So each of these will exhibit their own behavior based on the rules and assumptions you put into the model. Then when you run the model, the population effect, the population change will be the sum of what the individuals are doing. This is what gives it a bottom-up effect rather than a top-down approach. Then a little bit on the movement and the direction and speed that I talked about before. As that's one of the key components, because one of the things that the agent-based models do very well, and there are no other models that really can do this, it applies a spatial component to the model. Means that you can see how the population changes in space and time because you apply information on how it should change in space and time depending on the environment that is occupying. So the movement is usually a function either as of the environmental variables that it is from the grid cell that is occupying. It's also a function on the environmental variables of the agent surrounding. It means that it can sense what is in the near surrounding, and you define the area of sense. And then it can also sense other individuals around it. Means that it can obtain information on the agents in the near vicinity of it. So all of these things, based on all of these functions, some movement decision comes up later when the agent is deciding what to do. So that was a lot of talk about what is behind it. So let's look in the fridge. This is a simple agent-based model setup. It doesn't reflect any real-world thing, but it's an example. This is a very squared river basin where water is flowing down from the bottom, up and around a bench, and then we have a hotspot where there's some food available. Then we're going to release some agents into this environment, and they're going to go look for food, but they're going to follow the current. So basically, they overall follow the current when they're moving, but when they find food, they'll start eating it and consuming it. So they'll stay there, and their movement behavior is going to change. And when the food is done, then they're going to continue along the path down the river. So this is a very sterilized, stereotypic image of an agent-based model of what you can do with very few means. This is a very simple model. Something more complex is slightly more complex, where you have interactions between two types of agents. This is two agent-based models colliding. This is an agent-based model for predators, that's the square boxes, and for prey, which are the round circles. And the predators will swim around, look for food, and when they encounter food, then within their search radius, they'll start going after it, but not in a not directly. It will still be swinging a little bit back and forth, and then, but if they encounter it, it will consume the prey. So this is another good example of small things that you can do. Actually, very big things that you can do with very relatively simple algorithms, with is contained in these templates. So what you saw is all of them had some movement and some speed. And in these, usually in agent-based models, we operate with three different kinds of movements. The first one is called correlated random walk, which is essentially the basis for normal behavior when you don't have anything really to do. This is wandering around, and this will a correlated random walk is essentially that you will head in the direction of your nose plus minus some sort of a turning angle each time you move. That means that but it is random whether you move to the left or to the right. That is essentially what a correlated random walk is. This can then be changed into something we call the kinesis walk. This is where you change behavior based on the environment that you're in. This means that if you're in a bad environment, somewhere you don't want to be, you'll move in a specific behavior. In this, it's moving very much to the sides. This is you could call that search behavior, because it's searching for a better place to be. But when this then comes into an area where it wants to be, then it'll have a more directional movement. This means that it'll optimize its behavior based on the environment that it's in. And lastly, you can also apply something called restricted search function, where it'll search for areas around. Instead of just swinging around looking, it'll actively look by the sensory organs or the sensory algorithms that you put into it, and it'll head for the area mostly desired to be in. These kind of walks we applied in a model that is here. This is one of our macro model, which is macros migrating along the coast of Norway. They'll be migrating northwards to go forage, and at some point in time, they'll have enough forage. They'll be their body size will be full enough, or time would just have elapsed for them to go south again. And that looks more like this. You can see that there's quite a lot of agents that's been released. However, these agents here, they actually move a little bit. They are not correlated random walk as such. This is more of a kinesis walk, because what you see in the background, that's a habitat suitability index. This is something that we developed based on dynamic habitat mapping, which we based on our hydrodynamics. And in this, we try to simulate areas and we try to investigate areas where the mackerel wants to be in time and space, because it changes over time. And the macros are programmed to try to look for areas where they want to be, because the place they want to be, that's optimal foraging areas. They forage better there than they do other places. You can see they went up, and then at some point they returned and went down again. So this is more complicated modeling, because you involve different kinds of environment drivers. But all in all, it's a very good way of illustrating how a model would then work. Another option you have is this restricted search function that I told you about. This is a model we set up with illustrating how birds flocking behavior acts in birds. In this, we have a range of bird agent being released, and simply they move through this correlated random walk, all of them, except they're also assigned a rank of 1 to 4. The agents with the rank of 4 move independently of everything. They just move through correlated random walk. But the agents assigned with a rank lower than 4 will at some point adapt the direction and speed of an agent with a higher rank if it's in close vicinity to it. And by combining this together, we actually get a very nice structured way of illustrating how birds flocking can be created. I think it's always impressive of what this looked like. Yeah. A little bit under the hood for Mike for a Mike ABM lab. In different software, it looks different, but in Mike, we have this this template set up where let's see if I can make this work. Where we have this is a setup here, and this part here is what constitutes the agent-based model. This is example of the passive drifters, so they don't have that many things in them, but they're composed of this state variables, which is where you code what state variables there should be in it, composed of some constants. This is all parameters that doesn't change in time and space. Then we have restricted search area functions, which is the functions where it searches for anything that's nearby. Then we have the real cool stuff. That's these ones. That's the arithmetic expressions, which is everything that governs the behavior of the agents. So it is combining the parameters of all the other ones into these expressions, and this is where you tell it essentially what to do. And then you have this horizontal movement, which is the finalized direct horizontal and vertical movement of the agents, depending on whatever comes out of the things above here. So that is what it looks like in ABM Lab if you use it in Mike. So a little bit about possibilities. What can this be used for? What has this been used for in some of our examples? And for our sake, we use this. This is one of the examples we used previously, which is where we combine the migration of a hypothetical marine mammal along a coastline, and then we expose it to an anthropogenic disturbance. And then based on that, we can see we see a little bit on how we assumed a reaction in these ones. You can, of course, then test different reaction patterns if you don't know how animals react, or if you do know how the response pattern is for a specific species, then you can, of course, include that into an agent-based model, and then you can see how the agents are being displaced by a disturbance without actually having to disturb them in real life. This is, I think, very handy. Here the impact is a noise. This is a pile driving, and the pile driving here is a real underwater simulation of a pile drive using spherical spreading of the sound. And here you can see by this where they're actually just forced away because they don't want to be where the noise is too loud. You actually get some sort of a displacement from the area, and then you can calculate something on return rates as well. Likewise, This is an example from our macro model, where we have a seismic survey sailing back and forth looking for oil exploration possibilities. A seismic survey, if you don't know what it is, it's basically a very large vessel that's sailing with a very large array behind it, and the array is composed of some very large air guns that makes a lot of noise. And here the macros are set to respond to the noise if it reaches a certain threshold. And I think what is interesting here is there's the macros are swimming. The colors you see behind, that's a habit suitability, as we talked about before. I think one of the things that's actually kind of interesting in this is that you can actually see some sort of a displacement zone here, even though the disturbance is happening here, because there's this drift of agents along the line. And you see the displacement zones are actually drifting a little bit. So that's like kind of interesting to see how that actually affects. This has also been published in a peer-reviewed paper as well, this model. In Singapore, we have used agent-based models for studying larval dispersal and connectivity in the riverine basin there. So this, you don't see the particles because there's simply too many of them. So here they're dissolved into a concentration instead of viewing the individual particles. But as you can see, the connectivity here, they're more or less passive drifters. They will rise and fall in the water column, and at some point in time they'll settle. They'll go from being an egg to become a larvae, and from a larvae they will settle. It's coral larvae, these ones. So they will settle at some point in time. So this is a very nice way of investigating connectivity between a spawning site and potential settling areas. Last but not least, there's this. If you want to look away from animals and more into industry, agent-based models can also be used for studies on vessel traffic, for instance. This is simulations of ocean-going vessels and ship traffic there. It can be used to optimize shipping routes if you combine it with dynamic hydrodynamic modeling. But also, if you want to, there's projects going on studying collision risk with marine mammals and ocean traffic by just combining this with agent-based models on of marine mammals, and then you can actually study the collision risk there. So, in summary, agent-based models are bottom-up models that deals with the diverse composition of populations instead of assuming equality across everything. It can be used to model a large range of objects or individuals across multiple sciences and DHI at least, but others have the possibility as well to do this interesting framework where you can get the agents to absorb a vast amount of information from the environment based on the information you have available.
Well, thank you, Lars. Thank you very much, and thank you everyone who is still on the presentation for attending today. And we look forward to seeing you on another webinar. Thank you very much.
Thank you very much, and have a nice day.